Le Chatelier's principle. Now what does this mean? It means when a stress is applied, the system will always have to readjust, similar to how your body, to undergo and maintain homeostasis, it will readjust using different types of feedback loops to keep you in a state of equilibrium and healthy. So I'm just put here in a simple definition: when a stress is applied, the system will readjust to relieve that applied stress. Now, the important question throughout this video is going to be how. How does that happen? Well, first one is going to be if something was added to the system how do you think we would respond? Okay, if something was added to the system. Well, it's going to use up that added material as soon as possible. Okay, so it will use up that added material as soon as possible. I'll just put ASAP, as soon as possible, by moving direction. And we'll look at that shortly when we create a table chart about equilibrium shift. Okay, so the equilibrium is going to shift in some direction. So I'm just going to put this here: by moving direction, in order to keep this equilibrium afloat, okay, because of that applied stress. So this here is an example of that. When you add something to a system, you are applying stress. So how do we maintain that equilibrium? Well, we have to move the direction, okay, and that's going to be called an equilibrium shift. We'll look at that shortly in a table, like I said. But again, if it is being added to the system, we move direction, and within that process, we use up that added material as soon as possible. The best thing for you to see is by an illustration using practice problems later on in this video. So in case you're still confused, it's okay. Just we'll look at these little key points here before we start drawing out our table and doing these practice problems. If it is in the other manner, so if something was removed from the system, what do you think would happen then? Well, it will replace that area. That was removed as soon as possible. So it's pretty much filling up what was lost by moving direction. Same thing, by that equilibrium shift we'll look at shortly. Okay, so this is another example of this applied stress. If you remove something from a system, that is stressful. So if that removal occurs, we have to replace that area, substitute that area that got removed, okay, so that it can maintain equilibrium, maintain that homeostasis, okay, and we do that by moving direction of the equilibrium shift. Let's have a look at that table now. Start here on the left side. We'll start with the particular stress. Then we'll have equilibrium shift. This was what I was talking about when I said the movement of specific direction. And then the last column here will have an actual effect on the equilibrium constant. Remember our KEQ that we looked at in the previous video? You can see the link in the description to look at that video in case you still need a refresher, or you haven't seen that yet, it is a precursor, a prerequisite to this video. So this here will be the effect of EQ. Let's give it a shot. So we'll start a little bit shorter here, and then I'll elongate these lines as we go along. We'll first start off by, again, an example of adding a particular stress. Let's add to the system. So let's increase the product concentration. Okay, so I'm going to say an increase, again, this is concentration, right, for the product concentration. Okay, when we increase the product, where is it going to go next? Where is this equilibrium shift gonna take that material? Okay, well, it's gonna go in the opposite direction. It's gonna go towards the reactant. Maybe I'll write this over here, towards the reactant. In case you're kind of confused why, let me show you an example here. So I think we looked at N2O4 in the previous video. And that created nitrogen dioxide. So this is dinitrogen tetroxide. This is going to be nitrogen dioxide. And in order to obviously balance out this equation here, we just have to put a 2 here, and now we're good. Maybe we'll just look a little bit better. Okay, so 2 NO2 here. So if we have an increase in the amount of product, okay, so we increase this area over here, where is it going to go? Well, you should have already learned in previous grades about diffusion. Okay, think of that at the back of your head right now. If there is a high concentration over here, where is it going to go? It's not going to stay here. It's obviously going to go and alleviate that stress to maintain homeostasis. So it's going to go towards the reactant. That's what I mean over here. It's going to go towards the reactant. Okay, and there will be no effect on the EQ, okay, on the equilibrium constant. Next, we're going to look at a decreased product concentration. What's going to happen? Well, if you decrease this one, imagine if it goes lower, okay? Where is all of this, okay, going to go in order to alleviate that stress? It's going to go and fill up that area that got removed, okay, to maintain that homeostatic balance again, okay? So if this decreases, it needs to help out, okay? So now this is going to go towards the product. Again, no effect on the EQ. Remember in the previous video, okay, sorry, 2 videos ago about the introduction to the equilibrium, there was only one factor that can have substantial effect on the EQ, which was temperature. Okay, so right now, neither of these, okay, will have an effect on the EQ. Again, link is in the description for you to have a look. So that was products. Now let's do the same thing for the reactant. So let's say we have an increase of the reactant concentration. What's going to happen? Well, of course, if you increase the reactant here, now there's too much of it, okay? Where is that going to go in order to alleviate that stress? Of course, it's going to go towards the right, towards the product, okay? So it's going to be towards product. That's the equilibrium shift. So towards product. Okay, and again, no effect on the EQ. Next, we're going to look at a decrease in the reactant concentration. And of course, if this one is now decreasing, how do we alleviate the stress? We have to make up for it by going in that direction to help maintain that homeostasis. So then now this is going to go towards the reactant. And again, no effect on the EQ. So now we're done with the product and the reactants, okay? Now let's look more towards pressure. Okay, so for pressure, we're going to start with maybe an increase in pressure. When you increase pressure, where is the shift going to go? Well, in this manner, rather than saying towards reactant or product, we're going to talk about particle formation, whether it's going to go towards a fewer particle formation or a greater particle formation. When you have an increase in pressure, this means that it's going to go toward a fewer particle formation. So I'll put this over here, toward fewer particle formation. Now, think about it this way in order to remember this better. If you have an increase of pressure, this is going to increase a lot of kinetic energy, and the particles are going to be bouncing around everywhere. So if there is, when in a system where there is an increase of pressure, there's going to be a lot of this, bouncing around of particles. So if there's too many of them in a particular area, that is not necessarily good, because this is not in balance. It wants to go to an area to alleviate that stress, to alleviate all that pressure. So if there's all this pressure helping to bounce these, the thermal energy, the kinetic energy of all these particles around, how are we going to alleviate that stress? We got to go towards an area where there is less of them. So in particular in a party, let's say you're not particularly an extrovert, okay, more of an introvert, and there's a lot of people starting to come in, lots of loud music, it's starting to get a little bit rowdy, okay, that's a lot of bit of pressure, okay, then what are we going to do? We want to go towards fewer particle formation where there's less of them, okay, to alleviate that stress, that headache of just feeling claustrophobic or just not feeling very social. Okay, you want to go toward an area where there is fewer of them, so it's going to go towards fewer particle formation. That's an easy way to remember it. Okay, and in terms of the effect of the EQ, it's same thing. There is no effect. Now let's look at a decrease in pressure. If there is a decrease in pressure, this is going to be the exact opposite approach. If there is decrease in pressure, we want to go toward greater particle formation. So there's not enough wackiness going on, right? We want to get more social. Okay, you want to go not toward fewer particle formation, but you want to go toward greater particle formation. And again, this one here has no effect on the KEQ. Now let's put in pressure as well, okay, but the pressure this time is going to be for an inert gas. Okay, when you add pressure of an inert gas, there's actually no shift at all. Okay, and there's also, of course, no effect on the EQ. Why is this the case? Let's just put here as a side note for factors that don't affect this EQ shift. Let's first look at catalyst. We haven't written it out on the side yet, but we will. For a catalyst, it only increases the rate of the forward and reverse reaction. It doesn't do anything in terms of the shift. So we'll write that shortly. Just let me write it here on the side first before we talk more about the inert gas over here, because that's the point of this. So for a catalyst, it only increases reaction rate forward and reverse. For the second one here is what we're going to be focused heavily on, this inert gas, okay? So this inert gas, it's obviously going to be increasing the pressure, okay? But there's two things that I want you to take into account when we look at this inert gas, okay? So when you add an inert gas, so I don't know, and the one that I tend to be using a lot in the classroom, for an example, is Ne, neon, this inert gas, okay? Let's say it's at a constant pressure. Okay, how is this possible? When you add this gas, how can we maintain a constant pressure? How does that make sense? It doesn't, right? If you have a container and you add this gas, obviously it has a pressure, right? We've seen that over here. It has a particular stress of pressure within the walls, confined within the walls of the container, hitting off the sides, right? So if you add this gas, of course it's going to increase pressure. So what do I mean by saying that there is going to be constant pressure? Well, if there's constant pressure, what do you think the only tactic is possible in order to make that happen? Obviously, it's to increase the volume. So it's by increasing volume. Okay? And again, in the videos that I've shown you before, okay, about the ideal gas law, again, the link is in the description as well. By increasing the volume, you are going to be able to maintain the constant pressure because they are inversely proportional. Again, the link is in the description. Please have a look at the video prior to this one. Okay, so by increasing the volume, you are able to maintain that constant pressure. Okay, so that's one way. Another way is by adding the gas. Okay, same thing. Let's use that same example of Ne at constant volume. Whoa, okay? If you have a particular volume and it's not changing, but what the heck, you are adding that gas, which obviously is going to exert some pressure, this is kind of problematic, right? You're not changing the volume, so what do you think is going to happen to the pressure? Of course, the pressure is going to increase. There's no way about it, okay? So it's going to obviously by increase. So maybe I'll just put here, therefore pressure will increase, okay? Therefore pressure increases, okay? Because obviously since the partial pressure of each gas receives or remains the same because they're not affected by other gases. So this can occur as well. Okay, it really depends on what you're doing with the volume. Are you going to be keeping it constant, which will obviously agitate the container, the pressure is going to increase, or we can relieve the pressure by keeping it constant, but you have to make sure that you compensate by increasing the volume. So this is why these are factors that don't affect the EQ shift. So what can we put here in conclusion? When we say that there is no shift here, again, this no shift definition is not 100% accurate, okay? Because it really depends which realm we are looking at. Are we looking at this one to say that there is no shift, or are we looking at this one to say that there is no shift? So what do you think? Pause the video right now and have a little bit of a thinking session here. When I say no shift here, which most textbooks say, okay, are we looking at this condition or are we looking at this condition? Take a moment. All right, so hopefully we're able to figure it out. For the no shift, this one over here, it would be for this one. Why? Okay, because if we did it this way, what do you think is going to happen? We are changing the condition. We are increasing the volume to compensate. So of course, there is going to be a shift. You are literally actively changing the condition of the volume. So of course there is going to be a shift. You are manipulating what needs to be done in order that there would be a shift in order to maintain this constant pressure. You are actively seeking to do that. So there is going to be a shift. If you don't do anything and you keep it at that constant volume, sure, it's going to get a little crazy in there, a little hectic in there, but there is going to be no shift because you didn't actively change the volume in order to compromise for that pressure, okay? So this here would be no shift. No shift. This here would be a shift. Okay, but just in general, okay, to keep things simple for now, okay, until you get to a higher grade, okay, we'll keep it simple, we'll keep it as no shift, but I just want you to have in the back of your mind it's for this condition over here. Similarly, I wanted to touch up on the catalyst. Okay, we've written it over here, so let's put the catalyst here as well. So when we add that catalyst, okay, that stress over there, what do you think is going to happen? Well, there's no actual shift. Okay, why is there no shift? Because all it's going to do is get to the equilibrium faster. They're not part of the reaction, okay? So it just gets to the equilibrium faster. Okay, so maybe I'll write that over here, okay? Because there's no actual effect on the EQ, it just gets to the EQ quicker. Now let's look at the complex terms with temperature. This is where it gets a little bit confusing, but I'm going to try to show this to you and portray this to you in a way where it's going to be easy for you to remember and refer to so you can get a good grade. Let's say we increase temperature. Okay, then we'll do a decrease in temperature. But I also want to divide these under the effect of EQ into two smaller subcategories. So for our first increase in temperature, obviously, if you were to think about this in a way where energy is coming into you, okay? So obviously if there's an increase in temperature in your surroundings, where is it going to go? It's obviously going to go towards you within the system, right? So obviously if you're in a hot sauna and you enter into there, where is that temperature going to go? It's going to secrete into you, okay? Then you're going to start feeling hot internally, okay? So of course when you have an increase in temperature, think of this as an endothermic reaction, okay? So it's going to go towards you, right? Internally and towards you. So this is more endothermic. You're not releasing energy, you are taking in that energy in that sauna, okay? So we have towards the endothermic reaction, okay? And obviously for the decrease in temperature, that's the opposite. You are releasing heat, okay? So this will just be towards the exothermic reaction. Okay, let's bounce back up to here. So for an endothermic reaction, I want you to think of an endothermic forward and an exothermic forward. Okay, so I'm just gonna put it over here. I know this title here, okay, is endo reaction, so I'm gonna put endo up here first, okay? I know this one says exo, so I'm gonna put exo up here later, okay? So again, exo will be over here, endo will be over here, okay? And then these on the bottom, the not so important ones, okay, if I may call it that, are going to be the leftovers, okay? In case you're confused, don't worry about it. Let me show you what I mean by that. So when we talk about an endothermic reaction, I want to put endothermic up at the top, okay? That's the primary one. Endothermic forward reaction, okay? And then for the exothermic reaction, we're going to put it up here as well, okay? The exothermic forward reaction. Okay, and now for an endothermic forward, because it's supposed to be endothermic, think about it that way, the equilibrium shift, it's supposed to be endothermic. So in an endothermic forward reaction, because these kind of align really well because they're both endo, this is endo, this is endo, okay? So if they're both endo, what's going to happen? You're going to have an increase in KEQ. KEQ increases, so it's going to proceed more, okay? Now if we do it the same way this way, okay, if there is an affinity to go towards an exothermic reaction, and we've already put the exothermic forward reaction up here, obviously these align really well, so what's going to happen here? The KEQ is also going to proceed more, it's also going to increase, okay? So I'm going to put a KEQ is going to increase here as well. That's a great way to remember this table. This is the table that I like to use for my students as well, okay? So this here, okay, are going to align for an increase of KEQ, and this here will align to increase in KEQ in their respective type of reaction, as an endo or as an exo. So what do I mean by the leftover amount here on the bottom? The leftover amount is going to be the exact opposite of what we have on the top. So if this is endo forward, this here at the bottom is going to be an exo forward reaction. Okay, and this would be the exact opposite. Does not proceed in that particular direction that it's supposed to go forward. Okay, it's going to go the exact opposite. It's going to be KEQ decreases. Okay, same thing down here. What is the opposite of this exo forward? It is going to be the endo forward. Okay, so I'll put this down, endo forward reaction, and this is going to be the exact opposite. Instead of a KEQ increase, it's going to be a KEQ decrease. So this is a great way for you to remember things, okay? And again, the best way for us to understand this holistically is by applying it to an actual practice problem. So let's give it a try. Now, I would highly suggest you also screenshot this, take a picture of it, whatever, okay? So you took a screenshot of the previous chart, okay? This here is the continuation. Take this one as well so that you can refer this while we do the practice problems shortly. All right, state the effect of an increase in temperature on the following equilibria. So we have this as our chemical equation. Looking back on the chart, hopefully you have it, on file with you. You took a screenshot of it, or maybe you printed it out and you have it with you of what I just written out just prior a few seconds ago. Keep that chart handy. So we have this as a reactant, this as a product. If we increase temperature, we obviously want to categorize it. Okay, you should have that chart with you on the side. Okay, so look at that. So under increased temperature, what did we have? We had what? Toward endothermic reaction, right? So under this endothermic reaction, what happened? It was subcategorized into two different charts, okay? One on the top, one on the bottom, okay? So we had on the top the endo forward reaction, and this is where the KEQ increased, and then we had on the bottom the exo forward reaction, and this would be where the KEQ decreased. So what are we looking at right now? There was an increase in temperature, so we obviously have to use this row over here, and we also know that delta H here is a negative value, which means that this is an exothermic reaction. Okay, so obviously we can't continue to use this endo being aligned with that endo. Okay, we'll have to take a little bit of a detour and go towards the exothermic, okay, because we are dealing with an exothermic reaction over here, which means that there's going to be a decrease in KEQ. So rather than going towards the right to proceed, it is going to go in the opposite direction. It is going to go towards the left. State the effect of an increase of pressure on the field on the following equilibria. Okay, well, we remember when we look at this, when we have an increase in pressure, what do we write down on your chart? If there was an increase in pressure, what's going to happen? There is going to go toward fewer particle formation, toward fewer particle formation. Okay, and obviously we know that there's going to be no effect, right? No effect. So we look at this reaction over here. We want to count the amount of moles, okay? How do we know whether one is going to be a higher amount of particle formed or the lesser amount, okay? The coefficient, the moles, okay? So there's 2 moles over there, there's 2 moles over there, but there's 1 mole over here, okay? So there is going to be 3 over here, there's only going to be 2 over here. So what's going to happen if there is an increase in pressure? The increase in pressure is going to go toward a fewer particle formation. Which one is fewer? Obviously 2 is lesser than 3, so of course it's going to go in that direction. This is the answer, going towards the right. State the effect on the following equilibria if the stated stress is applied, okay? Now, we know that our heat is on the product side, so what does that mean? This is going to be obviously an exothermic reaction, okay? However, what is our particular stress? Okay, it is going to be an addition of oxygen. So if there is more oxygen over here, if you increase the amount of oxygen, like diffusion in your previous grades, how are we going to alleviate this so that we can maintain equilibrium? If there's too much here, where is it going to go? It's obviously going to go towards the right. I get to alleviate that stress. So that would be the answer. The answer is going towards the right. Then what is the effect on the concentration of chlorine if we decrease the pressure? Okay, again, we're looking specifically at what happens at the chlorine. So we have 2 over here, we have 2 moles over there. If you decrease the pressure, what's going to happen? Okay, remember, on a decrease of pressure, you should have your chart handy with you on the side. Okay, if there's a decrease in pressure, what's going to happen with the equilibrium shift? Okay, obviously it's going to go toward greater particle formation. And of course, no effect on the EQ, equilibrium constant. So, as we can see, they are the same. Greater? I think not. I don't believe so. There is no greater. So what's going to happen? Nothing's going to happen. This is your answer. Alright, these are the 2 green questions of the day. This here is the first one, and all of this here is the second question. Give this a try on your own, pause the video, and I'll be giving you the answer shortly. This is the answer to the first question. This is the answer to the second question.